Welcome back to a nice cool day in Thailand as the weather in mid-December now is starting to cool down and be very pleasant. What we're going to do today is continue on in the series of videos on the EV fuel gauge circuit board. This guy right here. Please feed the YouTube algorithm by giving the video a like. If you want to see more like this, click subscribe and ring the bell to be notified of new videos. If you want to chip in on my expenses, I now have Patreon and YouTube memberships. I want to give a quick shout out to my new sponsor, PCBX. It's a circuit board and board assembly company, which turns out is right on the mark for me. I saw a post for their Facebook page and was interested in their capabilities, so I joined the group. PCBX isn't as well known as some of the other circuit board companies, but they've got the facilities to compete with up to 8-layer boards, 2-sided SMT assembly, and over 200,000 parts in their catalog. They also offer their own design tool, but can accept native files from KiCad, Altium and Eagle, and of course, standard Gerber files. The interesting thing for me is that they happily support people like me who only need prototypes and low volume orders. Their circuit board prices are about the same or a little cheaper than the others, but they say their board assembly has better quality at a lower price. As a new customer, you have immediate access to great prices and big discount coupons for boards and assembly services. To top off the partnership, I hope to visit their Shanghai factory this winter and make a great video so everybody can see their capabilities. So be sure to check them out the next time you're uploading a board design. As you can see, hasn't changed at all since I left Barcelona, but what I want to show you today is the online menu system running in the web server on the ESP32. The purpose of this web page is to allow you to configure all the parameters of how the calculations take effect and do the right thing to handle the battery pack in your car. I didn't want to make a board that was inflexible and you needed to do crazy things to make it work in your car. So this is highly configurable in software, and I will walk you through all of the user interaction and the source code just to get an idea of how it works. Now, the code and the board are still in process. When I finish up this video, I'm going to jump on making version 0.2 of this board and send it off to manufacture, hopefully making a trip to China and a factory tour, and we'll just get the whole thing done right there in the factory of one of my sponsors. So cross your fingers that I can pull this off. So the software is actually in two separate parts. The first part is the getting the ESP32 onto the Wi-Fi network of your car. Once that's done, the rest of the software is configuring the web page here to set up all the parameters of how your vehicle works. So let me take you through a demo of each of them and then the source code that makes that happen. And the source code is going to be rough, but it works. You may see extraneous debugging messages and stuff, so don't worry about that. Ignore the man behind the curtain. So the first thing that happens when you power up a fresh board is the Wi-Fi manager software kicks in. This is a library that's available for ESP32, and it handles getting the board onto the Wi-Fi network in a very, very straightforward way that's been tested, and you just basically include a few lines of code in a header file, and you get all of this functionality for free. So you as the developer, you don't have to write from scratch the code to get your board onto the Wi-Fi network. So as you can see, I have a board set up called EV Fuel Gauge. That's a Wi-Fi network that's ready to go. What you want to do is join that Wi-Fi network. And this will take just a few seconds like it does on any other Wi-Fi network. Now what it's going to say is you don't have the internet, which is true. This is it's a home base router essentially with no active internet connection, but you don't care. You just want to connect to the board to set properties. So we are now connected to the ESP32. We jump into the web browser here at 192.168.4.1, and this is the hard-coded IP address on the Wi-Fi that you set up. And what you want to do is click Configure Wi-Fi. You want to put the password and Wi-Fi name of the Wi-Fi system in your vehicle. So what we're going to do today is simulate my condo network is my car. So we're going to click on Michael 2.4G. We're not going to save anything. We're going to put the password in and we're going to click Save. What it's doing now is it's saving the Wi-Fi network name and the password into non-volatile storage in the ESP32, and now it's rebooting and it is connecting now to your vehicle Wi-Fi network. Okay, let's take a quick peek at how we incorporate all of that powerful Wi-Fi management and sign up into the code. First thing you do is you include this header file, Wi-Fi manager.h. Then you go into your setup and we'll search here. And this is my setup routine. It's very, very straightforward. You create a Wi-Fi manager object. So you set the host name and then you call one line of code, auto connect. This is the code that handles everything we just saw, completely managed by that library. Selecting the target Wi-Fi network, entering the password, and reconnecting the board to that network. It all comes through here. That will complete with a success or failure, and you can do what you want there. When it fails, I decide just to restart the ESP32 so the user has another chance to enter the proper credentials. If you succeed, you can pull the user's chosen SSID and password and save those away. I debug a lot of stuff here. You can also pull out the board's IP address, which you will need in order for the user to connect to the board and go into the configuration screen. And then I save these things away and then continue on with the rest of my setup. That's as simple as you can get. Just this code here with a lot of debug and parameter saving. From within Platform IO, go to your PIO Home tab or pick it up over here and look at your installed libraries. Currently, I have two, the Telnet Stream for debugging and Wi-Fi Manager by Zapu. And this is the one you want. And I'm running version 2.0.17. So we will go into libraries. We will do a search, Wi-Fi Manager. And it's the very first one that comes up. This is the one you want by Zapu. And you can say, you can choose your version. The latest one works beautifully for me. You say add to project, and it even gives you sample code exactly like I showed you before. So that is all managed for you by Platform IO. Okay, I've just logged into the router managing my condo's Wi-Fi, and I found it right here. This is EV Fuel Gauge. The web page for the router doesn't handle the space properly. It's showing the, the conversion of it into a code instead of an actual space, but we know this is it. It is sitting at .129 on my network. So let's jump over. So in order to make the board and the software understand the battery pack in your car, you have to do some calibration. The first part of that is with your 12-volt battery system, because the 12-volt battery in a car is never exactly 12.0 volts. So I can't hard code that in to the calculations. So what I need you to do is put a voltmeter on your 12-volt bus somewhere in the car as it's sitting quietly doing nothing. You read the voltage on your voltmeter and you type that in here. Maybe it's 13.5 volts. And then you click calibrate. That will save away that 13.5 volt value, and it also takes a snapshot of the actual voltage of the 12-volt system at that time, and it uses that to calibrate the difference between what the 12-volt system is at the time of a reading while you're driving and how to apply that to the gas gauge needle. You need to do the same thing with your pack voltage. You read the pack voltage as the car is sitting still doing nothing, and you very safely read your pack voltage and you type in a value that you read off the voltmeter. And again, you hit calibrate, and it saves that value away in exactly the same fashion, uses it in the same fashion as a calibration of what the pack voltage is at any time that it takes a snapshot to calculate your state of charge. Then you need to do two additional things. You want to set what you would consider to be the lowest pack voltage that you want to comfortably have in your car, and this is the voltage that we will use to set where the empty needle is going to point. And you come up with a number, say you never want to go below 128 volts. You set that, that becomes your entry, your empty point for the gauge. And similarly, you do the high value, say 144 volts, and you click set. Those two values set up the point at which the gauge will be told to drive at the empty and the full point. Then we come along, and I should actually reorder this because you need to set the place where the board will read your pack voltage from. Most of you will just use a wired connection. You will safely wire the board to the high and the low value point of your battery pack. The board will safely read that value and apply the calculations. Some of you will be using an EVTV box called the V2, which is the EVTV battery management system if you use Tesla battery modules in your car. And if you have an EVTV V2, the board will read the values over Wi-Fi in a data packet driven manner that Jack and the guys at EVTV dreamed up. And the good thing with this is it requires no wire. So you can have the board anywhere in your car, safely not connected to the high voltage of your vehicle. And all the data will be read wirelessly over the Wi-Fi. And the next section is actually figuring out how to drive the analog gas gauge in your car. And you will not find any documentation on this if you search for your car. You have to do it by trial and error. And what we're trying to do is figure out the voltage that the board needs to output to set the needle in your gas gauge to point exactly to empty. And you might want to start by sending it 3 volts, and you click set. And you watch and see where the pointer is now pointing. Maybe it's a little higher than empty, maybe it's actually below empty. So over the course of a few readings and settings, you may find out that this is exactly the right voltage to set to make the needle of your analog gas gauge point exactly to the empty notch. You want to do the same thing with the full. Maybe it ends up being, after several trial and error, 11.76. So you would type that in. Now the board knows exactly what voltage value to output to hit the empty and the full point of the gas gauge, and then interpolate in between to show your 0 to 100% state of charge, which is essentially what the board is trying to do. That's its whole purpose in life. Then if your board, if your analog fuel gauge has a low fuel light that lights up when you get down to the low end of the gas in your car, the board will actually be able to drive that light also through a separate output. And what you do here is you enter the percentage of your battery pack state of charge where you want that light to come on. And you can set this to anything you want. You can set it to 10. You can set it to 15. You could set it to 20 if you really want a reminder for yourself that you always want to set a charge without going too low. So this is purely up to you. Now, as a programmer, I have set a lot of debugging messages in the code that helps me debug the board on the fly. And I do that through two different ways. One, I can just turn messages off in the code. Nothing in the firmware will output any debugging messages. Then the first way to do it is you can connect a USB-C cable to that connector on the board and read the messages over a serial port. And you can do that inside Platform I/O. It has a window and you can tell it which COM port to watch out for. Those messages will be reflected right inside the programming tool. Or there's an option to send exactly the same message content, but it will go over the Wi-Fi across Telnet port 23. And what you would do is set up a program like PuTTY, and you would tell it, please read Wi-Fi, Telnet port 23, and you will see those messages come through in a PuTTY window on your screen. And that's going to be separate from the Platform I/O tool that I use to develop the code. But if say you're working with me to debug some sort of weird problem that your board or your car is having, I may ask you to set this up to show me the messages that are coming out over Wi-Fi with a PuTTY program. The last thing we can do is go into simulation mode. If you turn simulation mode off, your analog fuel gauge will show the fully calibrated 0 to 100 state of charge of your battery pack as defined by all of these values up here. Or you can go into simulation mode. And what happens is I will cycle through pack voltage values from your low to your high. I will go from this voltage to this voltage, and I will cycle back low, high, low, high, low, high. And you should see the needle on your fuel gauge go from empty to full to empty to full, and hitting exactly the empty and exactly the full points as it swings back and forth. Because the simulation code is not driving a voltage to the gauge, it is simulating reading real pack voltages, and the rest of the system, the code that flows from there, actually properly drives the gauge based on pack voltage. So if you see a problem in simulation mode, it probably means one of these values is not, one or more values is not set up correctly. And it's not reading voltage, and it's not driving your analog gauge properly. So that's pretty much it. Let's go in and take a quick look at the code and see how these values are stored, and then how they're applied during calibration as we decide what signal to send to your analog fuel gauge. Well, of course, the entire configuration menu system starts with a web page, and I am not an expert web page writer. This was brutally difficult for me even to make that tiny little web page you saw and getting everything just right. But I managed to build the web page inside Platform I/O, and it doesn't give you a representation of what the page is going to look like. So I have this tab in my web browser that points to the actual file, the HTML file that is being edited in Platform.io, and I have Chrome render it for me. So when I make a change, I just pop over to Chrome, refresh this, and I get a view of what the page will look like. And you'll see that every one of these fields has a %s in it. And that's going to be important for us in a minute, as I'll show you. If we go back to the code, there's also a style sheet that goes along with that to set, colors and all that stuff. But again, that was not the easiest thing for me to build. But once you get this web page all set up, you'll see that each of the fields, all the input fields are tagged with an IV, an ID, a name, and a value. And the value here is %s, and that's why we're seeing a %s rendered by Chrome. Every one of these things that the user types into or we want to display has a %s. And as we pop over to the code here in main, you'll see that the web page itself has a handler, and this is handle main. This is part of the web server, which I'm sure you already know a lot about if you've done a lot of this code. So what I do is, as I'm building the web page to construct it and send it back to the user, I'm reading in all of these values. Every value on the page I read from the preferences system by a token, and that I have to keep track of these tokens and make sure that everything matches up from where I'm saving it, reading it back, and displaying it in the page. Then, and this is the magic, the way I get the parameters into the web page that is rendered to the user is I take advantage of that %s. And anyone going all the way back to C code knows if you've got an sprintf, you can take a string that has %s's in it, and all the things you list after that will be substituted in line for each %s. So every one of these is a displayed value on the web page, and I just do a giant sprintf, and then sprintf puts it into this buffer, final web page. I then, using the web server, send final web page to the user, and that's how everything gets displayed. And of course, to collect the parameters that the user types in, the web page is obviously a form, and the values come back through some handlers. I look at the parameters that are coming back, and based on their token, I extract the value and save it away in the preferences. And for every parameter, there's a section that decides what do I want to do with this, and it saves away every parameter along the way to the point where the full form is set, and we're ready to use that in our calculations. All right, let's take a look at how I apply the calibration when someone enters one of the parameters. If the argument coming back from the web page is to set the pack voltage, right? We do some debugging, I read the key, I save that away. Then I read the actual raw voltage on the pin of the ESP32, and that comes back in this variable. Then, because the ESP32 is so bad at reading analog voltages, the company that makes it, Espressif, they actually provide a library function that applies a calibration to the value you get from the pin, and it returns it back as a scaled and calibrated voltage level times 1000. So it tries to preserve 3 decimal places and comes back as an integer. But the problem with the ADC pins is that it's not a straight line. It's not linear. There's a big calibration at the bottom of the range and at the top of the range, and it's not very linear all the way through. So in order to make up for the hardware failings, they're fixing it in software, but it does come back with a real voltage on that pin. Then I go and apply the 2 voltage dividers I have built into my hardware. One is a 23.5 scaling, and one is a 2 scaling, and I get back the actual voltage that I think should be on that pin, and I save that away later, and then we use that when we go to display the value on the gas gauge. All right, we're at where the rubber meets the road, and we're going to move the dial on the analog fuel gauge. So I'm just going to jump through this a little bit, so bear with me. If we're simulating, I'm going to cycle through the pack voltage from high to low. That's all that. We're going to skip that. If we're not simulating, then I read the pack voltage, again on the input pin, apply all that calibration we saw before, and at the end I come out with a pack voltage value. Or if the user has an EV-TV V2 board and Tesla modules in their vehicle, I can read the pack voltage over Wi-Fi. I read the Wi-Fi, parse the packets. I look for the one that is assigned to voltage measurements, and I read the voltage there, and I come out with a pack voltage. So we're either simulating, we are hardwired, or we are reading Wi-Fi. This variable always has the pack voltage. Now, I calculate a state of charge based off that from the user's low and high values. This is a number from 0 to 100. Then I take a snapshot of the 12-volt voltage level, calibrate that, and then understand what the 12-volt value is right now. Apply the calibration factors that we took at the snapshot when the user entered their 12-volt value. And from this, I calculate the needle full voltage and the needle empty voltage. Then we go through and do more calculations to determine the pulse width modulation value for empty and full, map the current state of charge against the pulse width modulation values, and finally, I write the pulse width modulation value to the pin on the chip, which is connected to the voltage source of your analog fuel gauge. And the needle goes boop, and it points to the proper place in your state of charge. So this is the line that does all the work after all that calculation and calibration. And that's pretty much it. We've got a working circuit board, we've got calibration settings in the web page, and the software does all of the mapping and the reading and the writing to make a happy gas gauge. So that'll wrap it up for this video. In the next one, I will jump into version 0.2 of the hardware on the board. I've got an error to fix. I've got some expansions to make on CAN bus. I want to redo the power input sections and some other happy things. And then hopefully I'll go to China and get this thing made. So, see you later. Before we wrap up, I'd like to thank my Patreons and YouTube members, Peter Bouvier, Puppy, and Craig, for their ongoing support. I see that a whopping 96% of my viewers are not subscribers, so please go ahead and click that subscribe button because it really helps out the YouTube algorithm. Thanks and take care, and I'll see you in the next video.